Hello and welcome once again to our weekly Fronius webinar. Today we shall be discussing DC side safety and protection, the Fronius Perspective. And to do this with me today is my colleague, David Mwangi, who is a technical sales advisor for Eastern Africa, based in Nairobi, Kenya. And of course, myself, Cyprian Okolo, the technical sales advisor for Western Africa, and I'm based in Lagos, Nigeria. So just to give us an overview of the regions we support, as you can see, the regions covered in red, the countries or region supported by David Mwangi, which is much of Eastern Africa. And then for myself, the regions covered in blue, which is basically English-speaking West African countries. And then, of course, Mohammed Sidat, who covers the Southern Africa region, covered in colored green, as you can see. Of course, to tell us briefly about FSP Plus, these are sales partners that also double as country-based distributors. And of course, they cover most of the Sub-Saharan Africa region. They keep replacement parts in stock. And of course, they serve as a first point of after-sales service. So if you're in the Southern Africa region, for South Africa, first of all, we have Inomatic Solar and IBT Solar, who are FSP Plus in South Africa. And then for Namibia, we have Radio Electronic. And then for Zimbabwe, we have One Stop Solar. For Ghana, we have Tino Solution as our FSP Plus. In Kenya, we have CAT, Greenspark, and Knights Energy. Also to tell you here that Knights Energy are also FSP Plus for Uganda. In Madagascar, we have Mada Green Power. In Lagos, Nigeria, of course, we have our Components and Solutions rack. And then, of course, Mali, Bamako, Mali, we have a Sonikara Solar Electro. So these are FSP Plus partners that are based in the Sub-Saharan Africa region. And just to track back, this is not to say that the Northern African region are not covered. They are actually covered by Fronius Middle East. So this is just to tell us that we have the whole coordinate points of Africa actually fully covered by Fronius. Good. And then let's have a look at the agenda today. We shall be going through protection classes, DC isolation, take a look at DC switch, and then the Fronius solutions and retrofitting, what Fronius comes with in terms of DC side protection. And then going further, my colleague David Mwangi will continue from this point, providing us with information on lightning protection for PV systems, string fuses and reverse current, and of course a reverse polarity of strings. And then he will now be giving us further information beyond that. Okay, having said that, let's get on the way with our very first point of call for this presentation, which is protection classes. Because when it comes to protection, it's actually divided into various classes. So we shall be beginning with that so that we can have a very good view of how DC side or protection generally is implemented. So to start with, there are basically three protection classes. We have protection class 1, protection class 2, and protection class 3. Now for protection class 1, they are basically implemented for grounded circuits. Grounded circuits are basically circuits that have one hot wire or one live wire and then other cable or the other wire is grounded. So meaning that only one live wire. There's only one live wire, of course, and then the other wire is grounded. Then for class 2, we have double insulated circuits. Now for double insulated circuits, the best illustration for this would be, say, a hairdryer or a pressing iron per se, because you have cables connected inside of these devices or appliances. Now, the body of, say, a hairdryer is plastic, so it's an insulator already. Now, if there is any case where the live wire touches the body of the hairdryer, in this case, the person using it or operating it would not suffer any electrical shock because it has been double insulated. And mind you, even the cable before the cable sheets, before it enters the hairdryer, in this case, in this example, is already they're already insulated against each other. So that's what we actually mean by double insulation or double insulated circuits when it comes to protection classes. And then we now have the last class, which is the extra low voltage circuits. So basically, these are protection classes that are implemented for extra low voltage circuits. And extra low voltage circuits are circuits that have relatively low voltage. So we're talking on the DC side, we're talking about from equal to or less than 120 volts. And then on the AC side, we're talking to values equal to or less than 50 volts AC. Good. Now, in addition to this, the above protection classes are applied for both AC and DC systems. But for grid-connected PV systems, which is our point of concern for this presentation, the protection class 1 and 2 would suffice. So this means that we will be dwelling on protection class 1 and class 2 because that's where the grid-connected PV systems actually fall into. Good. So we're going to be starting with protection class 1. And then to provide adequate fall protection in this class, the following measures are usually taken. First off is a single isolation of cables and circuits. And then secondly, grounding of metallic parts, that is the chassis, in combination with an overcurrent or residual current monitoring device. So this is how it would look like as an illustration. Say this is our module, and then this is our overcurrent protection device. And of course, you have the metallic parts of the device, in this case, an inverter, a PV inverter that is adequately grounded. And of course, the cables will come in single isolation also. Good. So that's for protection class 1. So for protection class 2, in order to provide adequate fall protection for this class, the following measures are usually taken. Double or reinforced insulation of cables, and then additional measures are usually taken because of the fact that PV cables tend to get exposed to harsh environmental conditions, say heat, ice, and UV rays from the sun. So this could eventually lead to cable breakage within a 20-year period. So because of this, extra measures are taken, and these include isolation monitoring, which is integrated or implemented for PV inverters that has transformers. Basically speaking, transformer-based inverters. And then residual current monitoring. This is usually implemented for transformerless inverters, which is where Fronius actually come into play. Good. So this is basically illustrating what we are talking about: double insulated cables, and of course isolation monitoring for the PV inverters, both transformer-based and transformerless inverters. Great. So having covered that, let's now take a look at DC isolation. For DC isolation in class 1 system includes, in class 1 systems, one of the following measures is usually recommended to be employed, which is the GFDI, the ground fault detector interrupter, or the impedance grounding. So we will be going through each of them. So this is for DC isolation protection in class 1 systems. So going through the GFDI, A GFDI can actually be realized in different ways. It is common to use a DC fuse in the range of 1 to 3 amps, depending on the size of the system, of course. And then how it implements this protection is that if a ground fault occurs, the fuse or current monitoring device opens the connection to the ground. So what we mean is, from this illustration, if there is a ground fault, the fuse or the current monitoring device opens so that the fault current would not affect the PV inverter in this case. And then unfortunately, with this implementation, there is what we call the non-detection zone of GFDI. So the design of the GFDI actually has 2 inherent implications. It is not suitable for protection of humans because 1 amp can actually be a high value for human beings to be exposed to. Now, secondly, if the fault occurs in the earthed conductor, it is initially not recognized, and then afterwards, if another fault occurs, it has the capacity to result in a hazard. Good. So to remedy this, it is recommended that a class 2 protection scheme would be used. And then the GFDI must be able to disconnect the ground connection before start of operation and detect if there is a ground fault in the grounded part of the system, meaning that it should have the capacity to sort of literally scan the system and detect if there is a ground fault before connection or before the inverter is connected to, in order to operate. So that's basically what it means. Now, that's for GFDI. So the other class 1 protection for DC isolation is impedance grounding. Now, in this case, the system is grounded by high ohmic impedance, which limits the fault current to a certain less dangerous protection limit. Typical value for this is about 30 milliamps. So what this is saying is, instead of completely breaking the connection, it actually drops down the fault current to what I would say a user-friendly or a touch-friendly current limit, which is about 30 milliamps. So just to give us a sort of a typical value or an instance with current equal to voltage over resistance, if the impedance is typically in the range of 30 kiloamp, the impedance is usually in the range of 30 kiloamp. That is if the voltage is equal to 900 volts. So this is actually a high impedance level that can drop fault currents to considerably low current level, as can be seen illustrated in this case. Okay, so let's now go into class 2 protection systems. They're basically, we have them for transformer-based inverters and transformer-less inverters. So for the transformer-based inverters, the inverter, in this case, measures the impedance from ground, the impedance to ground from the positive and negative via an impedance network, as earlier described. So if this impedance value decreases to a value below several hundred kilo ohm, a signal will be displayed or will be sent, or a warning command will be sent. For smart transformer-based inverters, what usually happens is that once this value is noticed, once the impedance value decreases to a warning level impedance value, the warning signal will be sent. If this continues, it will send another command to disconnect the inverter. Okay, so that's for transformer-based inverters. For transformer-less inverters, the inverter measures the impedance to ground from positive and negative axis, and then before actually completing the connection to the grid. Now, during the operation, the RCMU, which is the residual current monitoring unit, detects residual currents on the DC side. So if the value exceeds 300 milliamp or rapidly jumps by a value of 30 milliamp, the inverter automatically switches off. So these are sensed as fault conditions. So if the value exceeds 300 milliamp, which is one condition, or jumps by a value of 30 milliamp, the inverter automatically switches off. Now, this function, we have to say here that this function cannot be achieved by a commercially available RCD, since such units do not detect these sudden jumps. And good enough, we have RCMUs implemented or integrated in Fronius Snap inverters. Good. Let's now talk about the DC switch. For the DC switch, there are actually isolation requirements that have been made. According to IEC 63647-712, IEC basically stands for International Electrotechnical Commission. This is actually the organization or body responsible for implementing electrical, electronic, and other technology-related standards and regulations. So this is, of course, widely accepted across board, and this is, of course, the standard across many parts of the world. So this requirement says or recommends or makes a requirement to have a means of isolation on the DC side. So coming to the details of such requirement, it entails that there has to be a means of isolation so as to allow maintenance of the inverter. And then secondly, the DC disconnector switch must be capable of to interrupt the full power of the device, and of course must withstand the maximum voltage. These are conditions that must be satisfied by the DC disconnector switch. And then, of course, there should be a provision of a combination of devices, including switch and, of course, DC blocks to actuate switching and isolation. Okay, so having said that, the previous slides were actually just to give us basic information on protection and its various classes. So now we shall be coming in with how Fronius solutions and retrofittings actually come into play to implement these protection subsequently. So for DC side Fronius solution for snap inverters, we actually have them in two classes. For the small snap inverters from 3 to 8.2 kilowatts, and then for big snap inverters that ranges from 10 to 20, that is for the SIMO, and then 25 and 27 kilowatts, that is for the Echo. Now, for the small snap inverters, we have DC surge arrestor, or what we fondly call SPDs, which is a surge protection device. We have it in two types. We have it in type 1+2, M version. M simply means multiple MPPT version. It's available as a retrofit kit. Installation is available and, of course, optional ex-factory. And we have hardware adaptations that makes it possible for retrofitting with ease. For the big snap inverters, we have 4 technical designs. These include the DC surge arrestor type 1+2 for the single MPPT and multiple MPPT versions. And then we have the SPD type 2 for single MPPT and multiple MPPT versions. One might ask, why would we have type 2, just type 2? Just to give us a summary of what these types mean. Type 1 offers protection against lightning, and then type 2 offers protection against overvoltage. So we have lightning arrestor and then the protection against overvoltage. And then, of course, in this case, you can see that it just has, for the type 2, just has overvoltage protection. So as my colleague David Mwangi will be discussing in the subsequent slides, it will come into play why some regions actually, installers in some region actually just requests for SPD type 2 only. Okay, so it comes or is available as a retrofit kit, and then installation X factory is possible. So just to give us an insight to how they are connected, as you can see, this is this SPD for small inverters and how they are connected. And then this is the SPD protection device for the big inverters. And then for the Fronius Gen 24 Plus series inverters, we have, of course, the protection in SPD type 1 plus 2. It's available as a retrofit kit, and no installation X factory is available. Then, of course, since that is the condition, it is, of course, available via ordering from our FSP Plus. So once you order it, it's readily available, and it is easily connectable, as you can see in this case. So this brings me to the end of my part of the presentation. So I will now be handing over to David, who will be continuing from this point. David, if you are available, please, you can continue.
All right, so thank you so much, Cyprian, for the first exciting part of the presentation. So I'll now be taking you through the second part of it, and we will start by looking at lightning protection for PV systems. So lightning, of course, forms part of the surge damages that can occur to PV systems. But just to give us a general overview of the various surge or events that can happen to PV systems. So we are looking at the most common damages as a result of surges. So this will be in the form, as you can see here, from, if you look at the section that is showing you the surges, is only 18% of the various damages can occur to a PV system. So, and therefore, the lightning that we are going to be addressing is going to be in this portion. So we can see other causes of damage are also slightly bigger than what can result as far as surges are concerned. But still, being knowledgeable about this potential cause of damage to your PV system is very, very important, that you take also preventive measures for the same. So these lightning strikes, of course, will happen through electrostatic discharge, through also switching operations. And this can result in damages both to the hardware and software. And inadvertently, that means also that the system is going to fail as a result of these transient surges from lightning. Just to give us an overview of the areas that are prone to lightning strikes, in this illustration or figure, we are looking at the lightning density, or what is referred to as NG, in terms of strikes per kilometer square per year. And in one moment around the world, there are about approximately 2,000 to 5,000 active storms worldwide. So, and therefore, as you can see in this chart, for all installers or customers within the sub-Saharan region, we can see that we have a relatively high lightning density. So we are talking about an approximate of about 8 to 18 thereabout strikes per kilometer square per year on average. And therefore, this is a huge potential for damage for PV systems within this area. And as my colleague Cyprian had mentioned, therefore, when you are choosing your OVPs, be cognizant of the fact that any installation within this region of Africa needs to be adequately protected with the right class of the SPD or OVP device. So in terms of what lightning strikes endanger PV systems, so here we are talking about both the direct types and the indirect lightning strikes. We're also talking about strikes that will happen within the region of 500 meters and also beyond these 500 meters radius. In case of a lightning strike, what therefore happens? So in terms of transient surges or strikes that are just happening for a fraction of a second, these are not too problematic. But once you get into an area whereby the current takes a bit of time to discharge, then this kind of long-term currents are the ones that are going to pose a threat for damage to your PV installation. This could be especially the inverters that have sensitive electronics inside. So in terms of the division of the lightning strikes, so we can see the formation of the lightning before it hits the target. There is the what we call the leader charge, and then the leader charge plus the catch-up charge will now build up the main lightning discharge. And also in this classification, we also have the impulse currents, and these are also sort of transient because they are just happening within a fraction of a second and they have disappeared. But what we have to be concerned about are discharges, like I have mentioned, that are taking a bit of time to dissipate. So as you can see on this scale, we have the time scale here in seconds. So any discharge in terms of lightning current that is taking above 1 second and beyond, even if it's not as high as the impulse current. So we can see that there are some impulse currents in this example, for instance, that are in the order of 30 kiloamps. But these long-time currents are in the order of just about 200 to 400 amperes. But because they are taking quite a bit of time to discharge, then they pose the biggest threat to damage for your electronic components as well as causing fires. In addition to the DC side of the installation, we also have to be aware that this kind of surges can also happen on the AC side of the installation. And the damage that will be most noticeable will be the damage of the varistors of the AC side of the inverter. And these are most likely going to be caused by indirect lightning strikes. So these indirect lightning strikes can also happen that a lightning discharge happens to the ground, and the earthing conductor that is connected to the inverter brings this kind of surge directly to the inverter. So that's one of the reasons why the earthing conductor is connected to the SPD or the OVP once it's retrofitted to the inverter, so that either way, whether it's dissipating or protecting any indirect lightning strike, that this SPD is able to take care of both directions. So on the AC side, these surges can also occur if there is a bad or missing connection of the neutral conductor. And of course, the best protection here would be by way of arresting these surges. If you look at how to then optimally protect your PV system, we have various ways of doing this. And the starting point will be a grounding system that will also ensure that there is potential, that is electrical potential equalization. And this is the base actually for surge protection systems, and it is advisable that the grounding resistance is kept as low as possible to a value that is less than 10 ohms. Then when it comes to the actual installation with the cables for the system, with the inverters and the modules, we do recommend no cable routing. Then you keep your cable loops as small as possible. And then you have to look at the kinds of cables that are used. Are they protected, like my colleague touched on in the beginning? The kind of protection that is used for the various cables, you have to be aware of this, so that then you separate the extra protected cables and those that are not too well protected. In terms of the lightning protection, the external lightning protection, you have to build, if you are in this area that we showed in the beginning with this illustration where we have high lightning densities, you have to build an interception system as well as lightning arresters. And within the PV system, this concept of external lightning protection has to be integrated as the overall protection concept. Then you observe all the requirements, whether these are normative requirements, and the best way to do this would actually be to do it in conjunction or consultation with lightning protection experts, because there are some experts who only do lightning protection work. And therefore, if you do realize that you're going to do your installation in an area that is prone to lightning, for you to be able to adequately protect your investment, it is advisable that you work in conjunction with lightning protection experts. In terms of internal lightning protection, or what is happening within a building or even within the inverter itself, we have to take measures so that we have potential equalization, and this is going to happen with SPDs. As my colleague also mentioned, we also have to be aware of the SPD topology that we are going to be using. Are you going to use the SPD type 1 or type 2 only? Are we going to go for SPD type 1 plus 2? Then, of course, these kind of OVPs and SPDs can be integrated within the inverter or within a building system for you to be able to protect the internal structures of either the inverter or the building. So what factors have to be considered, therefore, when you're talking about overvoltage protection as a factor of maximizing your system safety? So we have, like I've said, number one, consider internal protection, and this is through the potential equalization using the OVPs. And then once you are able to maximize your protection and potential equalization, then you can be sure that you minimize the probability of default or fault, and therefore, in terms of the system uptime, you can guarantee that this system is going to give you the highest yields, and you require no reinvestments. This in terms of having to exchange either inverters or burnt out inverter boards and so on. Something else that might also push you to consider OVPs are what the insurance regulations for your particular installation are saying. So some insurers do require that SPDs and OVPs are designed as part of the installation, so that to be sure that any damage is not caused to the system that can be prevented. Then in terms of how to retrofit, this is very simple with Fronius, already shown by my colleague Cyprian in the video. So we have a simple retrofitting solution, and therefore overall inverter protection is guaranteed also in terms of overall system safety. Just to give you now the topology of the various SPD types. We've only covered or touched on the SPD type 1 plus 2 and then type 2, but there is also another type 3. So the type 1 plus 2, of course, as mentioned already, will protect against also lightning strikes as well as overvoltage. So this offers what we refer to as the coarse and middle protection. So the lightning current arrestor and SPD within one device, that is. And this has to be done either at the feeding point at the energy meter, and this has a residual voltage of between 1,300 to about 6,000 volts. When it comes to type 2 SPD, this of course can also do a bit of lightning protection, but not as good as the type 1 plus 2. So this only offers you some middle level protection with a residual voltage in the range of 600 to 2,000 volts. So you can see also in terms of the voltage differentiation, the type 1 plus 2 is quite different from the type 2 only. The type 3 SPD offers what we refer to as fine protection of electronic devices. So this is something that can be integrated also for communication lines. So it offers effective elimination of small surges and can be done also in-house. But for you to be able to protect also maybe things like routers or internet installations from both direct lightning strikes or over voltages, then you have to do this in conjunction with either type 2 or also type 1 plus 2 for you to be sure that these big surges are taken care of when you are trying to protect also the other electronic installations within the site. Then we come to answer what is an overvoltage category. So we have to give here a differentiation that the overvoltage category is not the same, or is it not equal to overvoltage protection or SPD. In terms of overvoltage category, we have them ranging from category 1 up to 4. So we have 1, 2, 3, and 4. So in terms, the difference here is the peak voltage that each category is able to handle, and also the classification depending on the materials used. And here we are talking about the insulation resistance. So when it comes to category 1, we can see that the rated surge voltage will be, and this was also briefly mentioned, in the region of 1,500 volts for laptops and phones and stuff like that. But if you're looking at a Fronius inverter, the Fronius inverter will offer you both the category 2 and 3 on the DC and AC side. So on the DC side, the Fronius inverter is at category that is able to withstand 2,500 volts, and on the AC side, up to 4,000 volts. In terms of lightning, there is a notion that PV systems do attract lightning strikes, but this is actually a myth. This is not correct information. So a PV system on the roof does not increase the risk of a lightning strike, and this has been proven scientifically, because a lightning strike, if it does happen, it actually hits first the highest point of the building, and rarely in an installation, even on a rooftop installation, will a PV array be the highest point of the building. So therefore, the consideration has to be done in terms of lightning protection concept and SPD always, so that you know that either both the building and the PV installation are fully protected against lightning strikes. But it doesn't mean that because you have installed a PV system on your roof that now you are at a great danger of having or attracting more lightning strikes. It doesn't work like that. So of course, there are different country specific requirements and many international and national standards, also local regulations for different countries. So one of the standards that is mostly referred to is, for instance, the standard VDE 0100-712-534 from Germany. And in essence, this standard is talking about when a DC SPD is required. So as an example, as we can see here that in this particular standard, in the annex, there is a reference to a situation whereby if the distance from the incoming DC cable to the inverter is exceeding 10 meters, then you require to place, as we can see in this diagram, at least 2 SPDs. But if the distance is just less than 1 meter, 10 meters from the incoming DC cable to the inverter, from where that DC cable enters the building to the inverter, then you can comfortably just use 1 SPD for that installation. So let's now look at the reverse current in a PV installation. So in a characteristic PV module, when there is reverse current operation, then the solar cell operates like a consumer. So you are dissipating power within a solar cell or a solar module if there is a reverse current. So, and these reverse currents can occur in parallel strings with different open circuit voltages, and there can be quite a number of causes for different open circuit voltages. So it could happen that there is a short circuit in one of the one or more modules, or it could be that there is a short circuit in one or more cells of a particular module, or if there is a double ground fault in a module or within the cabling. So it could be also between that there's a fault in the modules as well as the cabling, and therefore you come to a double ground fault. And the consequences here of the reverse current will be a potential to destroy all the modules that are experiencing this reverse flow of current. In terms of the ratings for reversed current tolerance for PV modules, in general, it is expected that most PV modules can withstand something in the order of 2 times the short circuit current. Also, in the range of up to 3 times the short circuit current, this does not pose a great risk of damage to PV modules. As a matter of fact, the Fraunhofer Institute in Germany has done a lot of study with these short circuit currents for modules, whereby they exposed some modules to a factor of 7 by the short circuit current for up to 1 hour without any damage happening to the PV modules. However, we have to be cognizant of the fact that these reverse currents, as mentioned in the previous slide, have potential for damage either to the cells that are experiencing this reverse current or an entire PV module. So therefore, we have to take measures to protect the modules from reverse currents. And one of the ways that we can protect the modules is actually by integrating these string fuses. So a string fuse, just a description of how it looks like, includes of course 3 parts. There is the housing, which is has 2 metal contactors with an insulator. Then there is the fuse wire in the middle here that is responsible for triggering if there is a reverse current event or a reverse polarity event. And then you have the quartz stud within the fuse compartment. And this quartz stud is responsible for termination of any electrical arc that might start as a result of either a reverse current or a reverse polarity. So when you look at the profile functions of a string fuse, then we are talking about the ability for the string fuse to protect against both overload and short circuit currents. So therefore, the fuse wire reacts by melting if these 2 events happen. And also, it's very, very important because it's going to be a safety factor for your installation when you have a string fuse, because the occurrence of fires due to electrical arcs is going to be minimized by a string fuse that is integrating or has as its design core the quartz stud. In terms of the categories for the various string fuses, there are quite a number in the market. So here we are going to talk about 2 categories that are quite common. Category number 1 is what offers only part or partial range protection, what is referred to as AR. And the application is only for short circuit currents. So this is not a fuse that is recommended for use with PV installations or PV systems. As we can see here, the continuous current happens up to the nominal current level. And once the nominal current level is exceeded, then the operation enters into what is referred to here as the undefined or unsafe region. And before the turnoff or before the fuse melts, then we could have exposed the installation to a current in reverse that is in the order of 3 to 8 times the nominal current. So this undefined or unsafe area does not guarantee that the arc is not going to form. So if there is a reverse current, of course, this reverse current in most cases is going to cause overheating of the particular device. So this unsafe operation with an AR string fuse does not guarantee the termination of the arc that might start. There is also another category that we refer to as the GR that offers full range protection. And this is for both short circuit and overload currents. So these kind of fuses are the ones that are recommended for use with PV systems. So the same kind of analysis we can see here is with the continuous operating current up to the nominal current level. Then once there is an overvoltage or a short circuit current, then the fuse enters into an undefined or a safe area. As you can see, there is also a differentiation here. We can also talk about the amount of time the fuse takes to operate within this undefined, therefore safe or unsafe area before turning off. And because the undefined area with the GR fuse is much shorter than the AR fuses, then the GR fuses can guarantee a termination of the arc that might start as a result of an overcurrent or a short circuit in the circuit. So a further analysis of the GR fuses, which are according to the IC standard 609269-9. So, and I would like to emphasize here that once you start, when you're selecting your string fuses, only insist on using or getting these GR fuses that are recommended for PV systems. And these GR fuses will also be printed on their body, either GPV, and you will also have a symbol that looks like a PV module. So once you see this kind of abbreviation and this symbol on this fuse, then you can be sure that you're working with the correct string fuse. In terms of operation, just like I mentioned before, we can see that in the order whereby the nominal current is exceeded, we are operating up to 1.13 times the nominal current. This is the undefined area. And therefore, before we go much further at between 1.13 and 1.45 of the nominal current, then the fuse is triggering. And therefore, the triggering, as mentioned before, is by melting of the string wire or the fuse wire. And therefore, this fuse is going to guarantee a much safer operation for your PV installation in terms of the risk of fires. This graph is showing us basically what happens in the case there is an overcurrent or an overload of current happens. So the average current times are defined in terms of the turn-off time, and the turn-off time would be equal to the fuse time plus the arc termination time, as you have seen in terms of the operation within the nominal current segment of the fuse, and then what is the operation once this nominal current is reached or the threshold is reached. And therefore, this is what we are referring as the arc termination time. So in this particular example, we have a nominal operation with a current of about 1 ampere. And then we encounter an overload at some interns that is going to develop into 3 amperes. So for a safe operation of this kind of installation, we require that the turn-off time should not exceed 0.08 of a second. So this has to trigger very, very fast. And therefore, the formation of an arc does not even start because the ignition temperature of the materials that are involved are not going to be reached within this kind of a time frame. So this is why it's important to use this kind of fast-acting fuses for the PV strings. When you want to calculate the voltage as well as the current for your string fuses, there are a few recommendations that we can make on this. So the nominal voltage can be calculated as follows. So this is the nominal voltage of your string fuse, has to be greater or equal to the maximum DC voltage of the PV inverter, or more precisely, this can be arrived at by looking at what is the voltage efficiency of the PV generator at the lowest temperature. As we know, PV modules at lower temperatures then generate a much higher voltage level, and therefore the string fuse design can be precisely guided by what are the voltage efficiencies of your panels at the lowest temperatures that you can encounter in your location. For current calculations, the nominal current of the fuse, there are a few derating factors that have to be considered. In this case, we are considering 4 derating factors that influence the fuse characteristics. So we have, first of all, the alternating load factor, and this is a static factor for PV systems, which is equal to about 0.9. Then we have the interrupting factor, and this is static and is defined by the manufacturer. Then you have the temperature derating factor, which is dynamic depending on the various temperatures at which the fuses can operate. And therefore, these are also mentioned in the fuse data sheet when you look at the temperature graphs. Another derating factor that you have to consider for selection of the nominal current for the fuse is the fuse arrangements. So, and this is also a dynamic figure and depends mostly on the number of fuse holders that will be placed side to side. And therefore, the consideration here is also in terms of the dissipation of heat and stuff like that. And for string control, the fuse factor that is used is an average of 1. Yeah, so this can also be obtained from the average current time curves of the fuse that you're going to use. These are shown in the data sheets. So let's now look at the reverse polarity within a PV installation. As we know, reverse polarity can cause damage or fire at the termination point, as we can see in this photo. So this was an event that was caused by reverse polarity. So string fuses, of course, would prevent this problem by acting very fast, as we have seen. But we have to emphasize that the nominal current of the fuse should not be higher than the short circuit current of whatever is being protected. Because if the nominal current of the fuse is higher than the short circuit, then the fuse does not trigger, and therefore the effectiveness of this fuse is not seen in this installation. When it comes to the nominal fuse voltage, the nominal fuse voltage should be slightly higher than the string voltage, and this guarantees that there can be arc termination within the installation. To understand better the operation of reverse polarity, so in this diagram, you're looking at an operation that has no reverse polarity. So we can see that we have 5 strings operating together. So each string is delivering 6 amperes, and therefore to the inverter, about 30 amperes are delivered. And the nominal voltage, as we can see here, we are operating from each string at around 350 volts, and therefore the potential difference between plus and minus is also 350 volts. We can see here that we are also using a string fuse with about 12 amps and a nominal voltage or a string voltage of about 900 volts. So as we have seen also before, for you to guarantee arc termination, then the fuse voltage has to be slightly higher than the string voltage. When we encounter a reverse polarity in a fuse, and here we are talking about a reverse polarity that is going to deliver up to 3 amperes in the reverse direction. When the fuse is bigger than the ISC of the circuit, so the fuse current is bigger than the ISC of the circuit, then we don't have the fuse triggering, and therefore the effect of this reverse current can be experienced within the reversed section of the string, and therefore damage is going to happen with this within this section that has a reverse polarity. So we can see here, in the case of a reverse polarity, the inverter does not get any voltage delivered, and therefore production does not happen. So in the first photo, we saw some damage to the inverter PC board, and therefore, if the reverse polarity is happening within the inverter PC board, also that can also lead to some problematic operation for the inverter, if not damage. This installation or this example is showing us an installation whereby there is a reverse polarity with about 3.7 amps in a single string. But because the string fuse is properly dimensioned here, also in terms of the current and the voltage, we have the fuse triggering off. Yeah. So, and therefore this damage, this flow of current does not happen to this affected area that has the reverse polarity, because anytime there is a voltage drop, then as we saw in the beginning, that particular section of the string or the module will actually act as a consumer, and therefore, because of that potential difference, all the voltage is actually trying to go to this affected area. But because we have a string fuse here that is properly dimensioned, then that particular part of the array of the string is properly protected, and therefore you minimize your damage. So the only thing here that you're going to replace is actually the string fuse, instead of thinking about the replacement of maybe a few modules that are damaged as a result of the reverse polarity. So, and basically that brings us to the end of the second session. I would like to give you just more information before we end. In terms of further information, if you are interested to get further information for all our products, you can visit, of course, the Fronius website. There are a lot of downloads and useful materials there. We also have the YouTube channel that has an African playlist where you can get all the webinars that have been done in the past. So at your own time, you can revisit all the topics that we have covered. For instance, in 2021, also 2020, those topics are all there. So we encourage you to take your time and look at all the materials that are available for you. For further information, whether it's regarding technical issues, training, sales, and after-sales support, we have the contact information displayed here. But more specifically, if you want to get in touch with us directly, my colleagues Cyprian Okolo as well as Mohamed Sidat for their respective regions, then you have their phone addresses as well as email addresses. And for the East African region, you also get in touch directly with me. So with that, basically, we have come to the end of our webinar today.